Quítalo. No, esto fue en 2021 cuando tuvieron. Bueno, bienvenidos a la sesión C2 de Cisis, que es la sesión especial New Methods and Models to Study the Spread of Malware and Fake News. Yo voy a ser el chair, Ángel se disculpa, Ángel Martín del Rey se disculpa porque no puede estar aquí con nosotros por motivos personales. Entonces vamos a empezar con el primer artículo, que es Finding and Removing Infected Trees in IoT Networks. Los autores son Marcos Ebert Silva, Roberto Casado Vara, Ángel Martín del Rey, Esteban Jové, Héctor Quintián y José Luis Calvo Roger. Cuando quieras, Marcos. Intenta pegar el micro y si no dejamos uno de estos. ¿Vas a poder hablar en el micro?
Sí, sí. Vale, esto no.
Ah, que tiene otra cosa que no, pero no está el USB. No está el chip. Como si no me pongo el.
¿Qué es eso?
Vale, sí. Bueno. Vale, gracias a todos por asistir. Mi nombre es Marcos Ebert y os voy a hacer una presentación de nuestra investigación que se titula Finding and Removing Infected Trees from IoT Networks. Y tampoco pasa. Vale. Bien, primero una breve introducción. Actualmente vivimos en un mundo donde los dispositivos inalámbricos se encuentran por millones gracias al auge de las redes IoT. Además, hay una evidencia que nos dice que en los próximos años veremos cómo estos dispositivos se podrán contar por millones. Mientras que las medidas de seguridad se basan principalmente en medidas físicas. En los dispositivos IoT nos encontramos con un claro problema, que es la reducida capacidad energética y de cómputo de estos dispositivos. Es por eso que se abre aquí un gran campo de investigación sobre técnicas de seguridad a la hora de cómo contrarrestar diferentes tipos de amenazas en estas redes. Ahora a continuación voy a exponer una serie de motivaciones que nos llevaron a iniciar esta investigación. Bien, en primer lugar, la literatura actual trata diferentes medidas de software sobre certificación, a nivel de certificación de los diferentes paquetes de red que se intercambian entre los dispositivos IoT. Esto tiene una serie de problemas, por una parte la centralización de estas técnicas y por otra parte la sobrecarga de las redes IoT. Bien, además estos diferentes modelos tienen otras desventajas como son el tener que situar cortafuegos para filtrar estos paquetes de red en sitios aleatorios dentro de la red. Además, por último, podemos hablar de que las redes IoT actualmente son los principales componentes de las Smart Cities y, bueno, esto lo que les permite a las Smart Cities es ese intercambio de información, análisis y, evidentemente, esto requiere de una necesidad de seguridad y por eso nuestra propuesta pues, viene a intentar solventar este problema de qué ocurre cuando detectamos diferentes nodos infectados dentro de una de estas redes. Vale, ahora a continuación voy a entrar a exponer lo que es el algoritmo en sí, qué es lo que hemos hecho. Vale, el algoritmo se divide en dos partes. En el paper están llamados algoritmo 1, algoritmo 2. El primero de los algoritmos es el que hemos llamado Infected Spamming Tree Algorithm. Este algoritmo, que aquí tenéis la formulación matemática, básicamente lo que hace es generar el spamming tree del grafo de la red. Es decir, nosotros pasamos de un grafo de las interconexiones entre los nodos de la red IoT y al final lo que nos quedamos es un árbol, un spamming tree, es decir, un árbol que no tiene loops dentro de conexiones dentro de los propios dispositivos ni enlaces redundantes. Vale, una vez hemos creado ese árbol de la red, ese spamming tree, entra en juego el segundo algoritmo, que es el que hemos llamado Infected Tree Cat. Este algoritmo básicamente lo que hace es recorrer la red. En este caso hemos elegido que la forma de recorrer la red sea mediante la visita de nodos aleatorios. Cada vez que visitamos un nuevo nodo, lo que comprobamos es si este nodo está infectado o no. Si detectamos que está infectado, cogemos el propio árbol del nodo, es decir, todas las conexiones que salen y entran del nodo, y las marcamos como un árbol a cortar. Una vez hemos recorrido toda la red y tenemos todos los árboles de nodos infectados, es decir, todas las conexiones posiblemente maliciosas, lo que procedemos es a cortarlas de la red. Para testear este algoritmo que hemos desarrollado, hemos elegido dos casos de estudio. El primer caso de estudio, que es una Cluster Tree Network, básicamente es un tipo de red donde cada nodo solo está conectado a uno más, o sea, donde existe, digamos, una conexión en estrella de la red. Y en el segundo caso de estudio, lo que tenemos es una red, una Mesh Network, es decir, una red donde todos los nodos están interconectados entre sí. Vale. Una vez hemos presentado estos casos de estudio, lo que hicimos fue pues, probar nuestro algoritmo en estas dos redes. En el primer caso, planteamos esta red e infectamos los nodos 1, 0, 3, 7, 8, 17 y 18. En verde podemos ver cómo se marca el spamming tree que hacía la primera parte de este algoritmo, y en rojo tenemos los árboles de los nodos infectados. En la figura B podemos ver cómo después de aplicar este algoritmo, aquellas conexiones maliciosas, bueno, con los nodos infectados, están cortadas. En el segundo de los casos de uso, lo que nuevamente en verde podemos ver el spamming tree de la red, y en rojo esos árboles maliciosos, que en este caso los nodos infecciosos eran el nodo 10, el nodo 8, el nodo 9, el nodo 12 y el nodo 11. Y como podemos ver después de encontrar estos árboles de infectados y cortarlos, tenemos una red sin nodos infectados. Vale, como conclusiones que sacamos de esta investigación, bueno, hemos desarrollado un nuevo algoritmo que nos permite eliminar esos nodos infectados de una red independientemente de la topología de la misma. Bueno, esto lo que supone es un aumento de la seguridad en las redes IoT gracias a que podemos aislar los nodos infectados de los nodos que actualmente no se encuentran como tal. Bien, el haber usado esos dos casos de uso lo que nos garantiza es haberlo probado en las dos topologías de red más comunes en el mundo real, y durante la ejecución del algoritmo hemos probado cómo efectivamente todos los nodos infectados fueron cortados y el resultado era el árbol más eficiente de la red posible con nodos libres de infección. Como líneas de trabajo futuro, lo que pretendemos es optimizar el algoritmo para que tenga un coste de computación polinomial, y vamos a intentar considerar modelos de propagación del malware, tanto globales como individuales, para probar pues, esta eficiencia del algoritmo en otros casos de propagación del mismo. A su vez también planteamos... perdón, me quedo... Bueno, da igual, ya está. Perdón, me quedo en blanco. Sí, ya está.
Bueno, me han dicho que tenemos que hacerlo en inglés, así que si os parece pasamos a partir de ahora al inglés. Ok, any question for this paper?
Hi, thank you for your talk. At the end, you say the complexity of the algorithm is polynomial.
No, we pretend to make it polynomial.
Oh, sorry, yeah. So, what is the complexity currently?
Well, now we select we loop through the different IoT nodes randomly across the network. So we can see that it's linear, so exponential.
And one more question.
Eh?
One more question.
Yes.
In the second algorithm, you say you choose a node at random to see if it's infected.
Yes.
Why do you choose it at random? Is there any reason you choose it at random? Does it not matter what node you study?
We selected a random node. That's the question, no? Why we selected a random node? Well, it doesn't matter where do you start, because when you mark a node, you just queue it in a infected queue or in a clean queue, and also you have to take into consideration that this is a photo of a current T time of the network. so the network the infected nodes doesn't spread while you are using the algorithm.
Okay, thank you.
Any question? Any more question? No? Okay. No falla, se queda otro. Espera. Okay. Next paper. Titled Benchmarking Classifiers for DDoS Attack Detection in Industrial IT Networks. The authors are Marcos Silva, Roberto Casado Vara, Martín del Rey, Nuño Basuerto, Dani Burda, and Álvaro Herrero.
Well, thank you for joining me again in this presentation. Now I'm going to show you a brief presentation of our research entitled Benchmarking Classifiers for Denial of Service Attack Detection in Industrial IoT Networks. Nowadays the number of IT networks have spread around the world, not only in home environments but also in professional ones. And we have to take special consideration for the industrial environments. These environments are constantly suffering from different types of attacks, especially denial of service ones. And being able to correctly classify those network packets between IoT networks is essential so we can determine if our network is suffering from a denial of service attack or is just working as normal. Our motivation to this research, it's impossible to detect if we are suffering from a denial of service attack using the most common methods. This is because the number of devices and the topology of the network are currently changing and increasing in number. There is a need for a new paradigm that efficiently and reliable we can detect those denial of service attacks while it is adapting to the changing network topology. And in terms of this paradigm, we must select which of those available methods are the best for this problem. Now we are going to talk about the dataset that we have used to train our models. This dataset of the denial of service attacks was created using WireSat capture program. We have used a variety of IoT devices, not only home ones like cameras, microphones, but also industrial ones. And for classification purpose, network packets were tagged as denial of service attack or benign ones. And we have collected 485,000 records. The datasets has these following fields. Connection time, that is the time between two IoT nodes that the connection is alive. Source and response bytes. Every packet that is sent or received from one IoT node to another has a data body that has this response byte size. Missed bytes, it's a possibility that when you are sending one packet from one node to another, some of the bytes of the data are lost. Source and response packets, the data is divided in packets, so this is the number of packets where the data of each network packet was divided. And source CP bytes and response CP bytes, the length of the IP or of the sender and receiver of the packet is essential in some cases to so we can know if we are suffering from a denial of service attack or no. And now talking about the models that we have chosen, we choose to use 6 different classification paradigms. These are linear models with logistic regression model, instance-based models with k-nearest networks, support vector machines models with support vector classifier, tree-based models with decision tree, random forest, and extra trees, boosting models with ADA boost and gradient boosting, and probabilistic models with naive bias. The reason behind choosing these models is that they are the most common use in each of these 6 paradigms. Now, to evaluate the models, we have chosen these following metrics. There are the common ones like precision, accuracy, recall, and F1 score, but also we have used a new one that we have called true negative ratio. That is the ratio of packets labeled as benign attacks classified as that. After dividing the dataset in the train and test packets, we have trained all the models and then tested them with these metrics. And we can see this in this table. We can see all the metrics, but if we only look at the common ones, precision, accuracy, recall, and F1 score, all the models have a perfect score. But if we look at the new metric, true negative ratio, we can see that there are 3 models that have a third ratio. That means that they are not classifying correctly any benign packet. That's because we have an unbalanced data set. That means that we have a big data set with almost all the packets tagged as denial of service attack, and there were a few tagged as benign packets. As a conclusion, in this paper, we propose a solution to classify the network packets as denial of service or benign attacks. We have used 6 different paradigms, and we have found the best of them that can solve this problem. Well, we have used a new metric that allows us to test those models even if the dataset is unbalanced. Our work has several limitations, but this provides opportunities for future research. The future research will focus on extending that dataset, finding more relevant variables that allow us to find more different attacks, and we will try to classify all the packets not only in denial of service and benign, but also in those attacks such as CNC file download, CNC Mirai, and CNC Heartbeat and Okiru, that are the most common attacks in IoT networks. And that's all.
Well, this is a kind of interesting problem because the data set is imbalanced and there are 2,000 or maybe 3,000 or maybe 23,000 records. Did you hear me? Yeah? Okay. And in the other part of the data set there are maybe 500 or 1,000. So the classical metrics, precision, recall, and these kind of things, there is a fraction. In one part, in the one part of the fraction, you have 20,000, 30,000, and the other part you have 500 or maybe 100. This percentage will be near of the 100%. So you have to take a look in the confusion matrix.
Sí, es que no, ahora no va. Vale. No va más para atrás.
Pues empezar desde el principio.
Vale.
Hola, la tabla. you show a confusion matrix, you have the true positives, true negatives, and so. So this true negative ratio, if you show the patch level attacks, you can compare better the algorithm because all of them have 100% of accuracy. So you can compare that. In summary, you should put the confusion matrix
Yes.
in the presentation. Okay.
Well, sí, es que se tiene.
Okay, apart from these metrics, why you didn't use the AUC or curve? Because maybe in this case it's more interested because it's what the metric make is the capability of the algorithm to distinguish in between the both classes.
We took it into consideration after after making the paper, but for future work, we will take that metric into consideration.
Okay, thanks.
Anyone has any question? Any question? No? Okay, thanks, Marcos. Okay. Next paper entitled a Q-learning-based method to simulate the propagation of APT malware. Authors José Diamantino Hernández Guillén and Ángel Martín del Rey. ¿Has puesto? Aquí tienes.
Okay, thank you. I'm José Diamantino Hernández Guillén. I'm a professor at the University of Extremadura, and in this presentation, I'll explain how a type of malware, in this case, APT, an advanced persistent threat, can use machine learning techniques, in this case, Q-learning, to learn how to spread properly. I'll start with a brief introduction, then I'll explain the mathematical basis of the model and how it is used, and finally I'll explain some countermeasures. I'll start with a brief introduction. First of all, what's an advanced persistent threat? An advanced persistent threat is a type of very stealthy malware directed against one target. In other words, it doesn't seek to spread to as many devices as possible. It seeks to infect one target. This type of malware has increased a lot recently due to the lack. The number of APTs has increased a lot recently because of this type of malware is very dangerous. Early detection of APTs is one of the main challenges that scientific community faces. However, I'm not going to focus on detection. I'm going to focus on countermeasures. As a countermeasure, we can use a combination of honeypots and multi-target defense. Honeypots are used to lure malware, and multi-target defense uses different techniques and mechanisms which change over time. We'll see that the combination of both honeypots and multi-target defense can prevent this type of malware from learning. Next, I'll explain the mathematical basis of the model. This model uses Q-learning theory. This theory considers that at each instant of time, the agent takes an action U sub t and receives a reward A sub t at the same time that its state can change. To learn and to take good action, this formula is used. This formula is a weighting between the Q values at the current state and at the rewards and Q values at the future state. Mu measures this weight and gamma measures the impact of the future Q values. Next, I'll explain how this kind of malware can use Q-learning, can use this kind of machine learning technique. At each instant of time, the malware is located in one node. For example, in this case, the malware is located in this node, and in this case, the malware is located in this node. Then the state of the malware is different in this network than in this network. The possible actions are the nodes that are the possible actions are the neighbors of the node where the malware is. For example, this node has 3 possible actions, and this node has 1 possible action. Finally, the rewards are good if the malware finds the target node, and the rewards are bad in any other case. Once the malware has learned, it knows the best path to reach the target node. For example, in this case, the malware starts from node 33, and the target node is the node 31, and the orange node represents the best path to reach the target node. In this case, it's the shortest path because there are no countermeasures. Finally, I'll explain some countermeasures against this type of malware. If we use static honeypots, the malware avoids them and learns a longer path, but it still learns. However, if we use a dynamic honeypots moving around the target node, the malware can learn properly. How in this example? In this example, the malware can't reach the node 31. However, in this example, the malware reaches the node with a longer path. Finally, I'll explain the conclusion. The conclusion, it can be said that this kind of malware using machine learning techniques can be really dangerous. However, the combination of honeypots and multi-target defense can prevent this type of malware from learning. Thank you for your attention.
Jose, anytime. Anyone has any question? No one? Okay, thanks, Jose. Okay, next paper entitled on the statistical analysis of individual base SI models for, no, this one not. Okay, next one, stability analysis of a stochastic malware diffusion share model Authors Samir Yamarez Elias and Tocino Ángel. Samir. Mira, pues la presentación tuya y luego te mueves aquí con...
Perfecto.
Good afternoon. My name is Samir Yamazares, and I'll be talking to you about the work I did with Professor Tocino to study the stability of a model used to study the diffusion of malware in a wireless sensor network. So, first of all, I'll start by talking about the model we studied. So this isn't the model we studied, but this was our starting point. This is an established model which is used to study the diffusion of malware in wireless sensor networks. It's called the MDBCA. And I would have hoped that Professor Martín del Rey would have talked about it, but he's not present. So I'll give a brief summary. This is a compartmental SEIR model, so susceptible, exposed, infected, recovered. And it's a generalization of an agent-based cellular automaton model. So for this model, there is a known stability condition, which is that constant, the basic reproduction number, is smaller than 1. And this model is a deterministic model. So this means that this model cannot capture fluctuations, random fluctuations, which may occur in the spread of the malware. For this reason, Professor Tocino and I considered a slightly different model in which the incidence given by the parameter lambda was substituted by a constant plus some noise. This noise is used to capture the randomness present in the interaction between a infected in a susceptible node and also the chance of the infection spreading. So now we have, instead of a deterministic equation, we have a stochastic differential equation. This means that the solution is no longer a deterministic function, but rather it is a random function. In this figure on the left, we have the solution to the MDBCA, the deterministic one, and on the right we have possible trajectories of the solution to the stochastic one. So as you can see on the right, there are several different trajectories, which is a result of the fact that this model is now random. So our analysis focused on one of the most important qualitative properties of dynamical systems, which is stability. There are several different kinds of stability, but the one we focused on is the one called asymptotical stability in probability. So let me briefly explain what that is. We say that the solution of the dynamical system, which I denoted by X, is asymptotically stable in probability if it verifies two things. The first thing is that if the starting point of the dynamical model, so x0, is close to the equilibrium point in the figure xc, then the solution, the dynamical system, x, will stay close. In the figure, it stays at most at distance epsilon. And the second part, the asymptotical part, is that in the time limit, when time goes to infinity, then the dynamical model will converge to the equilibrium points. So that's the stability that we'll be studying of the stochastic MDBCA model. So how do we do that? Well, for this model, we have only one equilibrium point, the disease-free equilibrium point, in which all the nodes are exclusively susceptible. And similarly to in the deterministic case, we can somewhat simplify this problem by studying, instead of the nonlinear equation, we study the linearized equation. So if this were just a deterministic equation, here in the linear equation, we would simply study the eigenvalues of this matrix M, and we'd be done. However, in this case, we also have a stochastic component. So we have to work a bit harder to study the stability. So to study the stability of the linear equation, which will in turn give us the stability of the nonlinear equation, we can use a theorem which relates the stability of this linear equation to the asymptotical stability of the second moment of the solution to this linear equation. This theorem says that if the the second moment of the solution to this linear equation is asymptotically stable, then the linear equation is asymptotically stable in probability. Okay, so in summary, we're studying this linear equation. If we see that the second moment is asymptotically stable, we will have achieved what we wanted. So the second moment, which we've denoted by P, is given by this differential equation. Note that this differential equation is deterministic, not stochastic, because once we take the average, the moment, this is now a deterministic equation. Okay, so we want to see if P is asymptotically stable in the deterministic sense. So to do that, first we simplify the problem a bit more. We note that the matrix that describes the second moment is symmetric, so we only need to study the lower half of the components. These components in green. If we call Z the vector formed by these components, then we have this differential equation. So now what we have to see is that the solution to this differential equation is stable. And this is now a very simple linear deterministic differential equation. So all we have to do is study the eigenvalues of this matrix M. The matrix M is a block diagonal matrix. So we study the eigenvalues of each of the blocks, and after manipulating several inequalities, we reach two conditions which give us that all the eigenvalues are negative, which in turn means that the solution is stable. These conditions are this first condition on one of the parameters, which is also a condition which arose in the deterministic system. And the second one is that a certain constant, which we call the stochastic reproductive number, is smaller than 1. Okay, so in conclusion, with this study, we reached the following theorem. If those two inequalities I mentioned previously hold, then the stochastic MDBC model is asymptotically stable in probability. And consequently, we have that this constant R0 is a sort of stochastic analogous of the deterministic reproductive number. Okay, let's finish off with some numerical experiments to illustrate the results. So in these 4 plots, we have the 4 compartments of the model: the susceptible, exposed, infected, and recovered nodes. The thick lines indicate the solution to the deterministic MDBCA model, and the thin trajectories are trajectories of the stochastic model. So in this case, both the deterministic and the stochastic R0s, the reproductive numbers, are smaller than 1. So in this case, the solution to both the deterministic and stochastic models are asymptotically stable. They both converge to the disease-free equilibrium. As you can see, the susceptible nodes converge to 1. That's the proportion of the susceptible nodes, and the rest converge to 0. In this example, where both reproductive numbers are greater than 1, we see that the deterministic model, given by the thick lines, converges to the endemic equilibrium point, whereas the stochastic one is unstable. As you can see, it fluctuates wildly. Okay. In this third example, we have the deterministic reproductive number is smaller than 1, and the stochastic one is greater than 1. So, despite the fact that the stochastic reproductive number is greater than 1, you can see that the solution to the stochastic model is also asymptotically stable. And this reflects the fact that our theorem was only a sufficient condition for stability and not a necessary one. So in some cases, the stochastic reproductive number may be greater than 1, but the stochastic system may be stable, like here. And finally, another example where both reproductive numbers are greater than 1, but in this case, the stochastic model does in fact converge to the disease-free equilibrium. So this is indicates that in some cases, adding noise to the model, we can stabilize it. In this case, adding noise made the stochastic model converge to the disease-free equilibrium. Okay, well that's everything. Thank you for your attention, and do you have any questions?
Any questions, anyone? No? Okay. Thanks, Samir.
Yep, you're welcome.
Okay. Last paper entitled Quantum Solvent Composer, Automatic Quantum Transformation of Classical Circuits. Authors are Daniel Scanet Expósito and Pino Caballero Gil. Te puedes mover aquí con esto y con el ratón seleccionas ahí. Vale, muchas gracias.
Gracias. Perfect. Y aquí mismo. Okay. Thanks. Okay, so the work we are presenting is entitled Quantum Solver Composing, Automatic Quantum Transformation of Classical Circuits. It has been realized in the University of La Laguna by Daniel Scanet Expósito, myself, and Pino Caballero Gil. First of all, we are going to see some context of Quantum Solver. Quantum Solver is a quantum toolset for developers that allows the easy execution of quantum algorithms. And it is divided in modules. Quantum Solver Basic, that offers simple algorithms like Bernstein-Basserani or Deutsch-Jobsa algorithms. Quantum Solver Crypto has several quantum key distributions protocols like BBHE4 or E91, B92. Quantum Solver subroutines allows to run more complex algorithms like Shor or Simon algorithms. And Quantum Solver AI contains quantum machine learning functionalities. The last module, which this presentation is about, is Quantum Solver Composer, that allows simulating classical logic circuits using quantum circuits. Let's see some fundamentals of the proposal. First, we are going to define the classical gates. Not performs a flip of a bit, or is an addition where 1 plus 1 is 1, and is the simple multiplication, and Shor is the addition modulo 2, 1 plus 1 is 0, right? So here we have 4 basic quantum gates that we are going to define by its effects over the basic quantum states 0 and 1, okay? X gate is like a quantum knot, flip the bit. C knot is a control knot. It has a control and a target. When the control is set to 1, then the target is flipped, generating the effect of a quantum short. Swap is a really intuitive gate, just interchanges the state of 2 qubits. And finally, the CC knot gate is similar to the C knot, but using 2 controls. When both are set to 1, then the target is flipped. So
why do we need the control as an output of the CNOT gate? Let's talk about the reversibility. This property allows us to get the input of a function only seeing its output. Okay, for example, the X gate is reversible because we know that we can apply the NOT twice and then we get the input, right? But what about the classical OR? Can we compute the output, but you can restore the input? No, this is impossible because since three same values are generated by different inputs, right? So that's why we need to return the control value in the CNOT gate to differentiate all cases. Reversibility is a property imposed by quantum mechanics. Okay, so the implemented functionalities are set and reset method to initialize and restore the system, the basic NOT swap and show gates that are inherently reversible, another basic gates that needs ancilla qubits to be reversible, a conditional copy, if a control qubit is set to 1, then can copy the register in another register. And lastly, we have implemented the shifting operation because they are widely used in cryptographic protocols. So to sum up, an exhaustive study of theoretical basis has been carried out. A powerful open source tool has been developed to simulate classical logic circuits using quantum circuits, and some future work that we are already implementing is the addition of new and more complex logic functionalities and the development of cryptographic protocols using this tool to show useful use cases of the module. So thank you very much, and any question? Thanks. Okay.
Anyone? Okay.
Thank you for your talk.
Thanks.
So if I understood correctly, the main part of your work was to implement deterministic gates using reversible quantum gates?
Yeah, right. It's exactly this work. Is use the quantum paradigm to simulate the quantum operation. And you maybe are thinking, and what's the improvement of this of this thing? We are now looking for a way to code the classic information more efficiently using qubits. And then, if we discover this way to encode the information, maybe we, using this tool, can compute better.
And the gates being reversible are a necessity?
Yeah, can you repeat? What?
It's necessary for the gates to be reversible, or?
Are you asking for the reason that must be reversible, or?
Yes.
Yeah. That's a good question. When the quantum mechanics has that a circuit is like a quantum system, and it cannot lose energy, and the information in a quantum circuit is like the energy of the system, and when you has an amount of information at the beginning of the circuit, it has the same energy has to be at the end of the circuit.
Okay. And one final question.
Yeah,
Are there any gates which can't be represented by quantum reversible gates?
Okay, that's a really good question. Yeah, of course. When you, for example, measure a qubit, you are destroying the qubit because imagine you have a qubit that has 80% probability to you get a 0, for example, and 20% probability you get 1. Okay, when you measure, you maybe obtain a 1, or maybe you obtain a 0, and then your qubit, your quantum state, is completely destroyed. So this is it's a gate that destroys the qubit. You lose all your information.
Okay, thank you.
Thank you very much. Another question? Thanks.
Well, we finish this conference. Thank you for joining me in the conference. And remember that the dinner is at 9:30 if you want to stay at the dinner. So see you in the dinner or maybe tomorrow.